Alright, so this will be introduction to my topology playlist, and basically topology is really the study of spaces, and that's really a very compact way of saying it, because really what I'm going to be talking about is how different spaces, what the structure of the spaces are, how we can understand it mathematically, how different spaces relate to each other, what kind of shapes can we get in these spaces. But really, before I get into any of that, it's important to kind of have some sense of what exactly we're going to be talking about. And so for this video, I'll be talking about metrics, and specifically the Euclidean metric. Now, if I have a marker here and a marker cap here, we know we can take a ruler and get the distance between the two of them. Now, this is not the Euclidean distance. The Euclidean distance, of course, is given by this formula here, which I'll get to in a second. But Einstein said that our space is not Euclidean. It's a non-Euclidean space-time. And I might cover that later. But anyways, so that's interesting because our space is not exactly the same one that we learn in algebra, for example. It's similar, but not quite. So really, when you talk about metric spaces, there are certain properties that metric spaces have, and I will be talking about those properties in the next video. But for here, I'm just going to talk about the distance formula and why it's why it's important to kind of understand this before we go into anything else. So, like I said here with the distance formula, and the distance formula is really a function that maps from Rn to R. Remember that if you have n-dimensional real space, the distance formula is defined for every dimension, and the result that you get is always a single real number. The distance is always a single real number, and that's essentially what this is saying. Now, if I have 2 points down here, let's say we take any two arbitrary points along the real line, and so x1 and x2. We can find the distance between them by simply using this little formula over here. So we have x2 minus x1 squared to the 1/2. Did not write it so neatly. To the 1/2 like this. Now, of course, for just r, this is really not particularly exciting because we essentially can just cancel these two out, and we're just left with the absolute value of x2 minus x1, which is what we'd expect. This is a very familiar formula. And in R2, of course, we're just going to see our familiar distance formula again. We have x2 minus x1 squared minus y2 minus y1 squared all to the 1/2 power. Of course, here, these don't cancel out right away. We have to do what's inside the parentheses first and then take a square root of that. But this is the distance formula, and of course, we can extend this to R3, R4, so on and so forth. But this is the general idea. The distance formula works for any dimensions. And by distance formula, I mean the Euclidean distance. Because the Euclidean distance formula is a metric. It's the Euclidean metric, and metric essentially is a function that kind of generalizes what distance is. There's also the max metric, the discrete metric, the taxi cab metric, and there are lots of other metrics. Those are just the ones that I know off the top of my head immediately. But basically, those metrics are sometimes similar to the Euclidean metric, other times very, very different, and interesting to study those properties of these metrics. And of course, topology is used, like I may have mentioned this, topology is used extensively in theoretical physics a lot. For example, string theory makes heavy use of topology, specifically K-theory, which I will get into much, much later eventually, what K-theory is all about. But basically, that's pretty much the general idea. All we're really doing is we have a specific way we define distance. We're saying that the distance between 2 points is this. This is what distance means. We essentially make up the rules in a way what the distance is. Technically, I could just say the distance between these 2 points is something completely different. And for example, I'm just gonna do a little bit of a spoiler alert. For example, let's say we have something. If we take not the Euclidean metric, but what's called the discrete metric. So the discrete metric essentially is defined as the following. So let's say x is equal to y, which means that essentially they're the same point. If x is equal to y, then we have that the distance is 0. And then if x is not equal to y, then the distance is equal to 1. That's essentially what the discrete metric is saying. So basically, that means that if I have this marker cap here and this marker here, the distance between them is 1. If I go here, the distance between them is 1. This is, of course, assuming the discrete metric. And very interesting. I'll get, of course, much more into that later, and I'll formally define what metrics are, and we'll talk much more about it later. But this essentially is a preview of what I'm going to be talking about for the rest of the playlist, which will consist of probably close to 100, if not more, videos. Anyway, so I hope you guys enjoyed, and I'll see you guys in the next one.